ASME Section 8, Pressure Vessel Construction Code. Here we go through this by topics as it makes more sense. We have also rearranged it by sections. So both are same, but this practically is more integrated if you go by topics rather than by sections, because sections you have to jump from one section to other section to solve the same problem, whereas here we have gone by topics, so the sequence is by topics rather than by sections as structured in ASME Section 8. You should know about the general requirements. Several questions might come from this, and also it is mentioned in API 510. Remember that API 510 is basically based on ASME Section 8. Most of that is taken from ASME Section 8. So manufacturer is ultimately responsible for welding, NDT, fabrication, and testing of vessel, although it may be subcontracted, but eventually the manufacturer is responsible. Manufacturer fill in U1 form prior to preparing the U stamp nameplate or U form. Part manufacturer fills U2 form. These are in ASME Section 8. These forms, templates, to be accepted by construction inspector. Here, construction inspector means ASME authorized inspector, not API inspector, who also has the duty of verifying that the applicable design calculation has been made at the file, at the manufacturer's plant, the time of data report, when it is signed by the authorized inspector, and then after looking at these documents and normally looking at, the calculation is per ASME code, and also witness the pressure test, then the authorized inspector sign up the document, thereby authorizing the application or fixing of certification mark or U stamp nameplate on the vessel. Manufacturer attaches a nameplate with U stamp, and that's where U stamp coming from. So U1 is the form for manufacturer, and U2 is the form for the part manufacturer, who is subcontracted by manufacturer to make part of it. It may or may not need a U2 form then, if the manufacturer fabricates everything himself. For code exemption, what this code covers and what does not cover, you can refer to U1, 2, or it's easier to refer to Appendix A of API 510. It's the same thing. Because as I said, API 510 is based on ASME Section 8. Joint category and joint efficiency. To find the minimum required thickness for the maximum pressure or maximum allowable working pressure for a given thickness for a vessel with ellipsoidal head, you need to go to UG32C. And as you can see, there are two formulas. One is based on thickness and one is based on pressure. S is the allowable stress, E is the joint efficiency, and D is the diameter of the vessel. Okay, so in the exam question, normally the yield strength S and the diameter D is given. You are asked to find the maximum allowable working pressure. So you use the second formula given the thickness, or vice versa. So if pressure is given, you find the thickness using this formula. If the thickness is given, you use the other formula. The unknown would probably be the joint efficiency. Now, to find the joint efficiency, that depends on the location of the belt, not the type of the belt. So it doesn't mean it's a butt weld, it's a U type of belt, single butt, double V weld, or it's a fillet weld, or it's a lap weld. it depends on the location of the belt. And for the location of the belt, you need to go to UW3 that shows typical categories of A, B, and C and D. And this is sufficient for the exam. Definitely question coming from here. You have to remember that A is the highest category and D is the lowest category. As you can see here, C and D are flange weld or nozzle weld, and A and B. A is the longitudinal weld and B is the circumferential weld. Okay? So you have to look at this to find out where the weld is located. Longitudinal weld is A and circumferential weld is B. Then you should go to table UW12 to find the category of weld corresponding to the joint efficiency. For a double V butt joint weld, full radiography, as you can see here, if butt joints, double welding, so joint category could be anything, ABCD, 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 but it depends on the type of radiography. If it is full radiography 100%, then it's 1, the joint efficiency, E. If it's a spot radiography, it's 85, and if it is no radiography, then the joint efficiency is 0.7. Now you can see here is that this is also a butt weld, but single butt weld. It's not double welding, but it's a single welded butt weld. The joint efficiency is slightly less. For full radiography is 0.9. For spot is 0.8 compared to 0.85 on a double, and 0.65 compared to 0.7. So make sure you know where you find this table, UW12. Start frequenting this table, so in the exam it will be easier for you to find it when solving the question. If you cannot find it, the joint efficiency from the table, then you have to go UW11, which is highly unlikely that such a question come. But if you can't find it, you can understand any of these categories, joint description, then you have to go to UW11, A, B, and C to find which category the joint belongs to. For joint efficiency of seamless weld, E equal to 1, as we said, and the spot is 0.85, and for no radiography it's for joint efficiency of seamless weld, E is 1 for spot radiography and E is equal to 85 for no radiography. Now, some people, they ask if it's seamless, there is no weld, so why there is a joint efficiency? This is the weld that is welded, the head is welded to the shell, okay? This is not the head itself. So this might be a bit confusing. The seamless joint, that means the head is seamless. The head itself is not welded, but the head is welded to the shell. So it has got more integrity, and that's why for a spot radiography is 1 and no radiography 0.85. So some questions simply ask you for joint efficiency value, and some questions that need you to find the joint efficiency in order to find the maximum allowable working pressure or the design thickness T. The static head, the pressure gauge to read for hydro test is the one that is placed at the highest level, because that is the least pressure is showing you, not accounting for a static head. So every feet below that, you have to add 0.433 psi if you're using water with a specific gravity of 1. If the specific gravity is more or less than 1, then that should be adjusted by multiplying that. So maximum allowable working pressure at the top is less than as you go down, and the bottom is more. That's why ASME UG 98 states that the maximum allowable working pressure for a vessel is the maximum pressure permissible at the top of the vessel, because If it can withstand that pressure that is measured at the top, then it can also withstand the pressure which is more at the bottom. So it's a more onerous scenario here. As you can see, this vessel, so 3 feet down multiplied by 0.433 is almost 1.3. So this should be here at the top for 474.7 or something, 4.475. And as you go down, it's 3 feet below is 476, and then 34 feet down, you have to add the 31 feet here multiplied by 0.433 plus 476, which is already the pressure here. You get this number, and then say as you go, say from 60 feet to 40 feet, 100 feet. So there is a 40 feet difference here. So 14 to 0.433 is almost 16. As you can see, this should be like 516 or something, but it's 510 anyway. Maximum allowable working pressure is different at various heights or elevation, being the least at the top and the maximum at the bottom. Internal pressure, here you're not, internal pressure for cylindrical shell. So for that, you need to go for UG27. Remember that for ellipsoidal, you went to UG32. For this, there is a different formula. So this formula is different from what we just discussed above, slightly. So, but it still has, formula for calculating T, design thickness, and maximum allowable for working pressure P. So again, the same way. So be careful if he's saying ellipsoidal shell or cylindrical shell. This is slightly different. Thickness of shell under internal pressure. Again, UG27. This is a deciding formula because this is for longitudinal joints, and longitudinal joints calculation decide whether is what the thickness should be. Now, why that is the case? Because the longitudinal joints are under almost twice of the stress of, as you can see, this is circumferential joint. This is the formula for circumferential joint, and this is the formula for longitudinal joint. Now, as you can see on circumferential joint, 2 SE, whereas here is only divided by SE. So here the thickness you need for a circumferential joint is almost half of what you need for a longitudinal joint according to formula. Now, why that is the case, it's a bit might look confusing. First, I need to explain that if you got a stress, the stress is 90 degrees to the weld. For example, if you stress along, if this is a shell and the stress is along the longitudinal joint, the actual stress is applied on a circumferential joint and vice versa. So if the stress you have this way along the circumferential line, the actually is being applied on the longitudinal joint. Now, the stress, this stress is much higher, sigma C, than say here sigma 1, because this wants to tear the vessel apart. So, and it's called hoop stress. So the stress here is twice almost than this stress, whereas this joint only needs to keep the shell together. This stress on the longitudinal joint needs to keep the joint needs to keep the shell from bursting. Okay, and because the weight is applied here, so that also helps this joint, the circumferential one. So anyway, even if you look at the formula, circumferential joint is half of the stress almost, because it's got a factor of 2. Whereas longitudinal joint, the thickness you get in calculation is almost twice at this. Even if you forget about this part, minus 0.6 p and minus 0.2 p. So for that reason, um, longitudinal joints are the most onerous. Even the NDE examination acceptance criteria is more onerous than that. For example, undercut here is 0.4 millimeter allowed, whereas on circumferential joint, 0.8 millimeter undercut is allowed. So it's even more onerous acceptance criteria, and because there is more stress there. So that's the most important one. So once you find the thickness for longitudinal joints, that's the deciding factor. Now, external pressure, UG28, this calculation for external is significantly different from internal calculation, simply because under external pressure, the vessel is being crushed, while internal pressure wants to tear the vessel apart. And because of this crushing or buckling load, the length or height is important to the thickness ratio, because it's like a momentum being applied also there. It's not only crushing and buckling, there is a momentum, and external pressure problems are based on the thickness of the shell to the outside diameter ratio. This is called a slenderness ratio. It's like a tall building being loaded from the top. So if the height of the building, as the height of the building increase with respect to the cross section of the building, so it might actually buckle, and the buckling limit is 10. So if the OD to thickness is greater than 10, and there is another formula when the OD is less than 10. So there are two charts here in order to solve these type of problems. The first chart is used to find a value called A factor, and then that is used to find the B factor in the second chart. And once you found the B factor, you need to solve the problem using the formula in UG28 on step 6. There will be no calculation question. You just need to know these fundamentals for external pressure. So what body of knowledge says that in API, the inspector should be knowledgeable for the rules of design of shells and tubes under external pressure, and the inspector will not be required to perform external pressure calculation. You just need to know if they talk about A factor, B factor, and how that is solved, and hardly expect any question from that. So for vessels made prior to 1999, the test pressure was 1.5 times of maximum allowable working pressure. And for vessels made prior to after 1999, the test pressure is 1.3 times. As you can see, it's less. This is because the quality of fabrication has been improved over the years, and then they have decided to use the smaller safety factor actually here. Now, S test temperature and S design temperature. You know, the material's strength changes as the temperature increase, or the allowable stress changes as the temperature increase or decrease. So the strength that you are allowable strength that you can use depends whether the ratio of strength at test temperature divided by the ratio at design temperature. I think it makes sense. Don't need to explain it any further. So for example, if the design temperature is, say, the working temperature is like 600 degrees Fahrenheit, and you are testing it at ambient temperature is around 40-50 degrees Fahrenheit, and the strength is less, at 600 degree Fahrenheit, then obviously there is a factor here involved. So you divide this so to simulate the actual design situation or the actual working situation for test pressure. Okay, if it's working at ambient temperature, then that's fine. The ratio would be 1 here. KSA means 1000 psi, or MPa means megapascal. So it could be given in either way. Pneumatic test pressure shall be 1.1 times of the maximum allowable working pressure. So for any reason, if you can't do a hydro test, they do under exceptional circumstances, they do pneumatic test, and pneumatic test is a very dangerous test because the gases need to be compressed, and it's also much more time consuming because it takes a lot of time until the gas is compressed and the pressure is built up. It takes hours. And plus, if there is any leak or any failure or explosion, that works like a time bomb because you're compressing and storing a lot of energy in the gas. And once the gas is released, it's like a gas capsule. It just bursts. Whereas for water, the damage is not so much. So for that reason, you first pressurize it up to half of the test pressure, and then you increase it by 10% at steps of 10%. So you have 50%, and then 10% increase until the 1.1 times of the maximum allowable working pressure is applied. So the total step would be 6. This could be a potential exam question asking for how many steps is for pneumatic test, for pressurizing it. Now, once you pressurize to that, there is a hold time, might be 10 minutes, and some, depending on the spec, might be half an hour. See what the procedure says. Then you want to do a visual inspection to see that there is no leak, looking for any distortion or anything, using a bubble soap or a sponge to check that there is no leak, whatever. You have to reduce the pressure to maximum allowable working pressure. So for that, for example, if it is you're testing it and it's 1.3 times of maximum allowable working pressure, then we divide it by 1.3 and you take it to that pressure. So you bring it down and then do the visual. All calibrated pressure gauges shall have a range of 1.5 to 4 times of test pressure. There might be a question like this, or there might be a calculation type of question. For example, it says the test pressure is 100. So they bring, there are like 4 gauges with these ranges. Which one is not acceptable? So say if there is that your test pressure is 100, then you can use gauges from 0 to 150 at least, or 0 to 200, or twice the test pressure is normally preferred, but this is the minimum maximum range of pressure gauge. So you can use another pressure gauge 0 to 300, 0 to 350, 0 to 400, but if it is 0 to say 450, then that's not acceptable. Or 0 to 500 can measure it, that's not acceptable. It should be between 1.5 times minimum to 4 times maximum. Obviously 2 times is preferred. Metal temperature shall be 30 degree Fahrenheit, 70 degree centigrade above the mean design metal temperature for vessels that are more than 2 inch thick. Metal test temperature shall be 10 degree Fahrenheit above the vessel or vessel that have a less than 2 inch thickness. Okay, so this is during the pressure test. So to avoid brittle fracture, to be safe, test temperature above 120 degree Fahrenheit not recommended because obviously, Generally, metals up to 200 degree Fahrenheit, they don't face any loss in strength. But above that, they normally might, depending on the material. So to be safe, they say don't hydro test above 120 degree Fahrenheit. Painting and coating only after completion of pressure test, because if you apply the coating or lining or insulation and painting before pressure test, they might mask the leak. So it's always recommended that you should do it after pressure test. During pressure test, stress on bolts should not exceed 90% of the mold, bolt material yield strength, just to be safe. Obviously, this makes sense, because if it passes the yield strength during pressure test, if you're blinding some nozzles or this, so it's gone into plastic deformation, and then which is irreversible, which practically destroys the bolt and might break later on, or it has a different behavior. Impact testing, standard Sharpie impact test is 10 mil by 10 mil by 55 mil. As you can see here, the cross section is 10 by 55 and is the length. And there is a notch here with 45 degree, and it tells you all the dimensions here. UG 84.2, this table shows test temperature reduction if Sharpie impact tests are below the normal size. This is, you might not get this because of the size of that part. So if you got a reduced dimension, then you have to go to this table to see what is the conversion factor. And 84.4 shows maximum temperature difference between samples. So if you want your test to be valid, it should be within a range. Each sample, each set of tests are three specimens. Sharpie impact test shall be conducted at the minimum design metal temperature or colder. So normally they see the 10 years temperature if it is atmospheric, and the fluid temperature is not important, it's ambient temperature. The 10 years weather and the coldest day in the last, say, 10 years, and add 8 degrees centigrade to that, and that would normally be the mean design metal temperature. But overall, it all depends on the, what is the working temperature, what is the coldest temperature that would happen. So that would be the mean design metal temperature. And that is the engineer's job to identify. So 3 specimens. Now, there are 2 requirements here. The average should not be below the value that is required for that particular material. And then to find the value, you can go to this UG84. So there are 2 requirements. The average should not be less than that. The average of the Sharpie value. And also there is another requirement. None of these test results, these 3 Sharpie test results, should not be below 2/3 of the minimum value. Okay. So there might be a question coming asking, we got 3 specimens and the average, it's meeting the average requirement, the minimum value, the average of these 3, but one of them is below the 2/3 of that. So then in that case, the test is rejected totally, and you have to retest with another 3 specimens or deal with it. So look at this figure 841 and M, which is for metric system, and there is foot pound inch unit. So depending on the question you get the unit, you have to use appropriate table. You can see from these figures that any carbon and low alloy steel with thickness less than 10 millimeter or tensile strength less than 260 MPa do not need the impact test, regardless of the mean design metal temperature. These tables, figures and table graphs show you whether it is needed or not. Exclusion also from impact testing if hydrostatically or pneumatically tested or P number one, all of these requirements should be met. P number one, group number one or two, less than ½ inch thick if it is in curve A, and less than 1 inch thick if in UCS 66 curve. Uh, Design temperature between -20 F Fahrenheit and 650 F, and cyclic, thermal, and mechanical loading is not important here. You do not need to remember all this, just peruse and see where you can find. So UG 84 and UCS 66 are very important because UCS 66, there are figure and tables. So figures, if you can find it from figures, tables are numbered. So if you can't find in figures, like it's difficult, it's like a border case, then you use the tables. This is about determining if a particular material at a minimum metal design temperature should be subjected to impact test or not. The materials are grouped under 4 categories, A, B, C, D. Find out which group the material belongs. For these, look up under figure UCS 66 for the material group. So they will tell you what material it is. First, you find a group. Once you know the group, look at the figure and find out where the material can be located on the relevant groups curves based on the material thickness they have given and the mean design metal temperature. If the point located, because one shows one element of the curve shows, say the x-axis, the design metal temperature, sorry, the thickness, and the vertical one shows the MDMT. Then you know the material group, you get the points, you know x-axis, you know y, so you know where the point is located on the curve, and then you know the group. So if it is above the curve on that group, there are four curves for A, B, and C and D each. And if it's above the curve, you don't need a impact test. If it's below the curve, you need an impact test. Now, if it is a border case, you can't find it quickly, then you should go to the table where the numbers are. So you can compare the number and find it out. You can see from that curve that no material needs impact test if below 10 millimeter, provided the mean design metal temperature is not colder than 55 degrees centigrade or 48 degree, 55 degree Fahrenheit or 48 degrees centigrade. For P number one group material, if post-well heat treated when not required, you can add 30 degree to the MDMT when determining impact testing exemption. So this is a very interesting thing. So if you post-well heat treat a material when not required, you can get an exemption by adding 30 degree. You might or might not, but like you can add another 30 degree to the MDMT, and then based on that additional uh, 30 degree or MDMT plus 30, you can look at the curve and see whether still it needs impact test or not. Marking. So ASME marking is for vessel stamping. U1 form, as we said, is for complete vessel manufacturer, main manufacturer. U2 is for the partial data report. It's called is for the part manufacturer. So a manufacturer who makes part of it for another bigger manufacturer. Weld size for attachment, welds at opening. So you should be able to determine if weld size meet code requirements. For fillet weld, it's UW 16.1 for calculation and restriction. Uh, there wouldn't be much from there, but look at this figure, please, and to see how that's like made up. There might be a calculation question asking you to do a fillet throat thickness um, calculation using weld leg length or vice versa. And it's a simple multiplication or division of zero point 0.5 times, 7 times, because fillet throat thickness is 0.7 times of fillet weld leg length. Look at 16 UW16B, where the range and formula for various weld throat thickness are given. These are open book questions. You don't need to memorize, but should know where to find them in order to determine the required size of weld and opening. Now, we just brought a fillet weld. As you can see, one is the leg. So this is a leg, and this is a throat. And this is called the face of the weld, and it can be concave or convex, but this is a throat. And that's why they say theoretical throat is this one, and the actual throat is up to this arrow then, because it's a concave. So leg into zero point 0.7 is throat. Throat divided by zero point 0.7 is leg. This is all you need to remember. Service restrictions apply only to certain vessels. Um, for example, full radiography for lethal service. So they might ask you, you don't need to go to the code. You should know that if they say lethal service like H2S, SOVR service, full radiography. Joint category is based on joint location. Type of joint is based on how the joint was fabricated. So this is type of joint is different from joint category. Joint category is about location. Type of joint is how the joint was fabricated, like single butt weld, double butt weld, fillet weld, etc. Longitudinal joint E is the only joint used for thickness calculation, since this joint undergoes the maximum stress. That's twice of the circumferential stress due to hook stress. Um, there are some NDT related topics. UW51 is radiographic examination of weld joints. You do not just remember that you do not need a written radiographic examination procedure as long as the required number of wire or hole in the penetrometer can be seen. The radiographic sensitivity actually is okay. Radiograph is acceptable. So uh, because if you can see the IQI, that means the wire number there or hole number there. That means that is uh, the smallest defect or indication you can see if you can see that wire. So sensitivity, here is says density by sensitivity. Um, one spot per 50 feet length of weld if you want to do spot radiography. So that means one spot, like 6-inch minimum, it should be radiographic length. And there might be some calculation here. For example, they ask you if it is a spot radiography, if there is 75 feet. So that means first 50 feet, one radiograph, next one is 25 feet, one radiograph. So the number of radiographs are two. Or when it's 100 feet, again, is two because there are 250. Now, if it's 110 or 101 or over 100, up to 150, then it's three. Spot examination of weld joints, again, UW 51, 52. And there is also, there might be a question coming, like say size of rounded indication, is this much is acceptable or not? Now, if it is not full radiography, size of rounded indication doesn't matter how big the size is. Okay, if it's a spot radiography. So, and then the last one, I think we talked about all this. Let's see, RTI acceptance criteria. Um, Then we brought this page 148. You go to UW, do we talk about this? Joint efficiency 1 for full radiography, 85 for a smooth, 70.7 for no radiography is a double welded. You could go to tables. Just we brought this 0.433 psi for every foot below. Maximum allowable working pressure is at the top of the vessel, so it's important that this can be an exam question. For ambient temperature pressure test, obtain conversion factor. We talk about this, why we need this, because we want to simulate the design condition. So we want to see if, say, for example, the allowable stress at uh, design is uh, more than or less than the test temperature. So you have to use this conversion factor here. So to simulate the actual design. Thank you.